All right, I think we'll get started. I realize I'm between you and the reception and the drinks, so I think we'll get started and move things along here. So my name is Keith Stewart. I'm a specialist solution architect. I'm specializing in our EMR, or Elastic MapReduce platform. This presentation is titled Interactively Querying Large-Scale Datasets on Amazon S3. An alternative title here is Presto on EMR. Okay. So what I'm going to do is cover these points. We'll start by looking at the challenges that are typically faced when using traditional data warehouses to query large-scale data sets. And then we'll contrast that with an alternative non-data warehouse approach. And this non-data warehouse approach is the focus of the rest of the presentation. We'll next look at the high-level steps that you would go through to be able to query large-scale data sets that are living on S3. We'll look at some of the components of this alternative solution, specifically Amazon S3. We'll drill down a little bit into that, EMR and how it can work with S3. Apache Presto, which is the secret sauce for querying large data sets. We'll look at how Presto can be deployed on EMR very easily. And at the end, we'll run a demo and show you how we can take this 29-year data set, US air flight data from the Department of Transportation, and be able to have that data on S3 and be able to run a query across this very large data set. So you'll be able to see it in action. All right. So when querying data on a data warehouse, there's a number of challenges that you face. In particular, the whole premise behind data warehouses is that you're implementing a schema on write. What that means is you're taking the variety of input data that you want to later be able to query, and you're processing that in a significant way to structure it in order to write it to the data warehouse, to the schema, in a highly defined, fairly rigid schema in the data warehouse. And there's a lot of work to do that. And once the data is in the data warehouse, then it's available to business, BI people, data scientists, et cetera. But the implications of this model, though, are that you're using specialized, often proprietary data technology, the data warehouses. And because of all the effort involved in taking all the data and trying to extract it, transform it, and put it in a form that can fit into your universal schema, there's a significant time delay before people have access to that data to be able to query it. Also, because it tends to be more expensive because it's proprietary solutions, the data warehouse. Also, the schema, because you're using this universal schema to store and manage all the data, that puts certain constraints on the types of queries that you can execute against the data. Okay, so the schema on write, this model for data warehouses, is the older approach to querying large data. An alternative to this is a schema on read, and so in this case, what you're doing is taking diverse sets of data, lots of different data sets, and immediately storing it, okay, in its raw, original, high-fidelity format. So you're taking all this data and immediately storing it in a distributed fashion in a cluster, okay? And typically that's an open source Hadoop cluster. And then on an as-needed basis, depending on the query, on a query-by-query basis, a subset of that data will be read during the query in its raw original form, read and structured on the fly to satisfy the query. Okay? So that's the schema on read. So you're deferring the structuring of the data until you actually execute the query, okay? And so there's a lot less work because you're typically looking at subsets of the data, and you're doing less work on the data because you don't have this universal schema that you're trying to pigeonhole the data, okay? Because it's open source, Hadoop, the cost is dramatically lower than a data warehouse solution, which is a specialized proprietary. And because the data, once it's stored in the distributed cluster, it's immediately available to data scientists to be able to work with and without any further delay. So the benefits are shorter time to answer, higher agility, lower cost, and because you've got the original high fidelity data, all of that data in its original form immediately available, there's flexibility in the types of queries that the data scientists can ask. They can query the same data in a variety of ways because there isn't this rigid schema that's organizing it. Okay. All right, so at a high level, what's it take to take large-scale data that's in S3 and being able to query it in a high-performance fashion? There's basically 6 high-level steps. First of all, you put your data in S3, and we'll look at a variety of ways in which that can happen. You configure and launch an EMR cluster with Presto. You log into the cluster, and then you tell Hive, the Hive meta service, you tell it about the data that it already lives on S3. You expose those tables, or expose that data as tables. Once that's done, then you can issue queries, SQL queries, using Presto against that data. Okay? So you're declaring or exposing the existing data in S3. You're not having to transform it or copy it or anything like that. It's simply a declaration step. So you issue the SQL queries and you get your results. So fairly straightforward. So let's talk about some of the components to this alternative to data warehouses. So the key component really is Amazon S3. Amazon S3 is a massively parallel object store. It can store anything from a single byte text file to a 5 terabyte video file. So it's very, very diverse in what it can store. It's scalable and elastic. So whatever amount of data you have and you send to S3, it'll accommodate it. You don't need to pre-provision capacity. You don't need to worry about growth in your data. S3 will automatically handle whatever new data you send to it. It's highly durable, 11 nines of durability, so you don't need to worry about losing your data. It has effectively an infinite inbound bandwidth. As I said, it's massively parallel. And it's extremely low cost. This really changes the economics of large-scale data management and querying. It's 3 cents per gigabyte month, or about $30 per terabyte month. As you'll see, S3 is kind of a foundational service. It was the earliest AWS service, but it's a foundation for a whole host of other AWS services. And it's been compared to the O'Hara airport in terms of being able to interface with all kinds of other services. It's a hub, really, for all kinds of data. In addition to those capabilities, S3 also has things like lifecycle management. So if you're accumulating data on a continual basis and it's growing rapidly, you can establish policies, bucket policies, or lifecycle policies, where beyond a certain threshold of age, the data will automatically be moved out of S3 and into cold storage, our Glacier, AWS Glacier storage. And that gives you an even lower cost profile. That's about 0.7 cents per gigabyte month. So you can set these policies up, and they'll take care of any old data that needs to be held on to, but not necessarily kept in active queryable form. And there are other things like triggers and so on. AES 256-bit encryption, both at rest and in transit. Whole host of capabilities for S3. So, as I said, S3 is a foundational service for a lot of other AWS services. You can exchange data, both reading and writing, from all these different services. We'll take a look at EMR specifically, but Kinesis Firehose is a way to get data from somewhere in the internet into the cloud and into S3 in a highly parallel sharded fashion. Data pipeline you can orchestrate workflows that move data among different AWS services, including S3. Redshift, the data warehouse offering. NoSQL databases like DynamoDB, relational services, RDS, and as we announced last year, Snowball, import-export Snowball, are these appliances, 80 terabyte appliances that we can ship to customers, and they plug into their network, copy their data locally onto the appliance, and then have that FedExed to AWS and put into the data put into S3 for them. And of course, Spark streaming and other things like Storm can interface with it. So S3 is very versatile. You can think of it as future-proofing your data. Once it's in S3, there's a variety of things that you can do with your data. And we refer to that as the data lake. The data lake is this schema on read. You take your data from a wide variety of sources in diverse formats and store that in high fidelity form in S3. So what does it take to expose that data once it's in S3 so that you can do these high performance queries? Well, this is a little snippet of a screenshot from the AWS Web Console in S3 in particular. And I've got this data set, flight delays, and I've got a path that shows that this is where I've stored CSV formatted data. And I've included some additional path information. This year equals some value, 1987 in this case. Doing that, in other words, spreading your data across S3 partitions, leveraging distinct information in the path, helps you maximize the parallelism of S3 and avoid any kind of hotspots. The more entropy, the more uniqueness you can have in the path to the object, the better chance that it runs in a separate I/O process. So it maximizes the parallelism. At any rate, this is a sample file here, the CSV. It's been compressed with bzip2. Compressing data on S3 is a best practice in addition to partitioning. That allows, it minimizes the I/O time because data can move back and forth much more quickly. And you know, if you think about S3 as a massively parallel object store with lots of parallelism, and you've got cluster technology, EMR, for example, the nodes in the EMR cluster can query that object store in parallel. So you maximize the parallelism. And so these best practices of partitioning and compressing the data can really help. And you can also transform the data into more efficient formats. Our demo will actually, instead of using CSV, will take advantage of Parquet. And Parquet is a very popular column-oriented data format. What that means is that when you perform queries, if you have SQL queries that have selects on certain columns, only the data in those columns are touched. That's in contrast to a traditional row-oriented data organization where the entire row has to be handled in order to get the data that you're asking for. So column-oriented is particularly good for wide tables, wide sets of fields, and that's another best practice. All right, so once the data's in S3, how do you make it known and available to other systems? Well, you can do that by running Hive, and you can run a create external table statement. So this is a DDL, and what you're doing is essentially declaring that this location, this bucket and path, the flight delay, CSV in this case, is going to be interpreted as a table. Even though they're flat files and they're compressed, it'll treat it as a table. And so the way you do that is you do the create external table, declare the attributes that correspond to the fields. You indicate something about the format of that flat file. In this case, it's a comma separated, so we're indicating it's separated by commas, there's some escapes, and the records are terminated by new lines. And most importantly, we're specifying that this table lives at an S3 URI, in this case, flight delays CSV. So that, when executed within Hive, declares that data as being accessible as a table. In this case, we call it air delays. And you can prove that it exists by asking Hive to describe that table. And so you'll get results coming back like this. Okay. All right, let's talk about EMR. So EMR is AWS's Hadoop as a service. It gives you scalable Hadoop clusters that you can scale in a variety of ways. You can pick different EC2 family types. You can have memory optimized for things like Spark and Presto as well. If you have a lot of number crunching, statistical calculations, machine learning, those kinds of things, you can use a CPU optimized EC2. If you have a lot of data that's disk intensive, you can use IO optimized. So there's different EC2 family types that you can leverage. You can use different EC2 sizes, different numbers of cores, different amounts of RAM, et cetera. And you can scale the cluster to whatever size is appropriate to your workload. We have a variety of applications that are available through a mere checking of checkboxes, and you'll see that shortly. We have 15 different applications currently, and we continue to add new Hadoop applications to that. And as you can see, Presto is one of the applications that you can readily deploy. It's a managed service. So you have the EMR automation takes care of spinning up the EC2 instances that are part of your cluster. It takes care of all the wiring, the configuration, the communication among those, and also will monitor the health of the nodes in the Hadoop cluster. And any node that dies, EMR will automatically replace that with another node. And even if a node is still live, but it's very slow, the EMR will detect that as well and replace it with a much more active one. And in the process, it will redistribute jobs to handle and restart jobs to be able to recover from any failures in the node. You can pay for it in a variety of ways. You can pay with the traditional on-demand EC2s, with reserved instances, and then spot pricing. Spot pricing is a real bargain. You can often achieve an 80 to 90% discount compared to on-demand EC2 instances. And leveraging spot within EMR is as simple as typing in the bid price that you're prepared to pay. And that's it. EMR will take care of spinning up grabbing those instances and making them available to your cluster. There's a variety of persistence or data sources that EMR will work with. Of course, HDFS, the traditional Hadoop data store. Most importantly is S3. But we also now have EBS volumes that you can mount on EMR nodes. And for those workloads that need to be PCI or HIPAA compliant, we have end-to-end security available, everything from encryption of the host disks Of course, S3, where the data lives, is AES 256 encrypted, both in transit and at rest. One of the most unique and powerful features of EMR is a component called EMR-FS. So EMR-FS is the file system. It's the abstraction layer that allows Hadoop applications to talk to a variety of persistent stores, but most especially S3. Okay? So EMR-FS is optimized for S3. It gives high performance reads and writes, direct reads and writes to S3. It's not copying the data to HDFS. What it's doing is actually reading and writing directly to S3. So from S3 to the CPU memory and back. Okay? Of course, intermediate temporary results can be written to HDFS, particularly for MapReduce applications. Using S3 within EMR, within the Hadoop on EMR, is as simple as changing the protocol in the URI. So your URIs use S3:/ instead of HDFS. That's it. Once the data's on S3, you can access it with that minor change. EMR will work with the encryption that S3 provides, both server-side or client-side. There's a variety of ways in which you can manage the keys. It's optimized for listing of the metadata for the objects on S3. So we've done a lot of work under the hood to make that transparent and high performance. And you can still use HDFS if you want to. In fact, you can have an application that simultaneously reads from S3, reads from HDFS, and writes to either one. Okay, so why is S3 such an important, and EMR-FS, which enables communication with S3, why is that such a powerful capability? The biggest impact is that it allows for decoupling of storage from compute. Okay? This is very different than an on-prem cluster or even a Hadoop cluster that you deploy yourself on a fleet of EC2 instances. When you deploy on-prem or you deploy a fleet of EC2 instances and you're leveraging the HDFS storage on those nodes, you are requiring a certain binding, a tight coupling between the amount of CPU, the amount of storage and RAM. You have to determine how many nodes you want to give you the aggregate memory, the aggregate disk space, and the aggregate CPU power. So that tight coupling in a traditional Hadoop cluster means that when you scale the cluster, when you store more data, you add more nodes. But that also means you're adding more CPU and RAM, which you're paying for. Okay? So that tight coupling in a traditional Hadoop deployment is very limiting. With this decoupling of storage and compute, you have a whole host of flexibility. So with the data stored in S3, because it's elastic and it's highly parallel, that storage is able to grow to handle whatever amount of growth in your data you see. Okay? So on the storage side, you've got a lot of flexibility there. On the compute side, if the data is stored in S3 and we have 11 nines of durability, that means that you can actually, you have a lot of flexibility in the sizing of the cluster. So you can, in fact, have a cluster that starts out a certain size, does its job, and then you can shut the cluster down. So you can actually terminate your cluster because your data is safe and sound on S3. The input records are there, the computation generates records that go back to S3, and then you can terminate the EMR cluster. So that ability to shut it down gives you tremendous cost savings, particularly in a batch model of workloads. Okay? You also have the ability to resize. You can have different size clusters. You don't have to worry about the size of the cluster for data storage. That's handled by S3. You worry purely in terms of what kind of SLA, what kind of time window you need the computation and processing to complete in. Okay? And very interestingly, you can run multiple EMR clusters. So you could have, for example, a separation of development, test, and production. Okay, you get 3 separate clusters. You could have a small development cluster that your data scientists can work on. You can have a separate cluster that's representative of production in terms of size that your software QA team can test. And then, of course, in production, you can have as large a cluster as you need. Okay? But they can all point to and work with the same data set that's in S3. So there's a considerable flexibility there. The other thing you can do is if you have a variety of workloads, instead of provisioning one cluster with an amount of capacity for your biggest job, you provision a cluster that's appropriate for the type of workload that you're doing, the one workload you're doing. And the second workload, you might require a bigger cluster, so you can have a bigger cluster, but they both work with the same data set. So there's a lot of flexibility. You can right-size the compute in a variety of ways. Okay, so let's actually go ahead and spin up an EMR cluster to show people how straightforward this is. Is it readable? I guess it is. All right, so we're in the create cluster here, and what I'm going to do is actually go to the advanced options. All right. And I mentioned we have 15 applications currently that are available through a mere checkbox. And so we're going to make sure we select Presto, and that's all we need on this screen. We'll go with defaults for the rest of it. We're not going to submit a step. We'll go next. So this is where you specify the amount of hardware, the number of nodes and the size of the nodes. We have a whole host of EC2 types, as you can see, broken out by different family types. So you can pick those. We'll go with a single master, a couple of core nodes. They manage the HDFS. There is some intermediate data that will be stored on HDFS. And then we're going to boost the task nodes up to 10. We could attach EBS volumes if we wanted. We could specify spot if we wanted to. In that case, we would be prompted for, I guess it's hard to see on my screen. We'd be prompted for our bid price, and that's all we would need to be able to take advantage of spot. We'll just go ahead with 10 nodes there. All right, we just need let's give this a name here. Let's call it Summit Demo. We'll call it Presto Demo. All right, and that's all we need there. And we're going to SSH into it, so we have to specify a key pair, and the rest of our fine is defaults. That's it. Now we're spinning up an EMR cluster, and it reminds you and summarizes what we've asked for. And if you wanted to sit and watch the hardware come up, you can do that. We're going to continue with the slides and let this cluster come up. All right. Okay, so the other piece of the puzzle, the other key component to this non-data warehouse alternative is the Apache Presto software. This is open source software. Hadoop is open source. So again, you're avoiding the expensive, proprietary, specialized data warehouse software. You're leveraging something that's very inexpensive. What is Presto, and where did it come from? So Presto was developed by Facebook in 2012. They designed it to work at petabyte scale data, and they designed it to be able to execute SQL queries. Okay. Originally, they designed it to avoid the slow map reduce step of Hive. They wanted to be able to examine Hive tables without having to wait for MapReduce jobs. That was the original motivation. But ultimately, they evolved it into a full-scale data query engine on its own. And they open sourced this as part of Apache in 2013. What are the benefits? So the key distinction is it's an in-memory distributed query engine. So as I said, it avoids the MapReduce step. The next slide will make the point why that's so important. But it's an in-memory engine that's very powerful. It was designed explicitly to support ANSI compliant SQL. As you may know, Hive and Pig and other query engines that are part of the Hadoop ecosystem are not necessarily ANSI compatible. So this was a big design focus. It was also designed to work with a variety of data sources using different data persistence technologies, and also to be able to execute queries that can pull data simultaneously from multiple data sources. And most importantly, was designed to provide rapid responses on the order of seconds to maybe less than a minute. Okay. So what's been achieved so far with Presto? So they've accomplished high performance, about 10 times faster than Hive. As a proof point, there are many companies using it, but as one proof point, Netflix is a huge user of Presto. They run about 3,500 Presto queries per day on a data set that's 25 petabytes in size that lives on S3. So Netflix has in fact standardized on storing their data in S3. That's what they use as their data warehouse. Because of the many benefits that we talked about. And they have on the order of 350 users actively using it at the same time. Okay. It's evolved to support a variety of plugins, different persistence engines listed there. BI tools can interface with it using JDBC and ODBC. And different clients can talk to Presto in a variety of protocols, but particularly HTTP and JSON. And there's a variety of languages that can interface with it. Very powerful is the ability to run complex SQL queries, things that couldn't be done with Hive and Pig and other query engines. This includes things like joins, aggregations, roll-ups, a variety of functions, windowing functions, etc. This is a high-level architecture for Presto. It runs on a cluster. The cluster is comprised of a coordinator and then a bunch of workers. A client will talk to the coordinator and submit SQL queries using different protocols. We'll actually, in the demo, use the Presto command line client running on the cluster itself. And then the coordinator receives the SQL, parses it, analyzes it, and then plans the execution, distributing the query across the set of workers. Okay. And in this diagram, it's showing data persistence on HDFS. But very importantly, it's showing that it works with the Hive Metastore, which is a central directory of data sources within Hadoop clusters. A little more detail. I mean, there's a discovery service. So all the components, the coordinator and the worker nodes register with the discovery service at startup. And then the sequence of events is shown here. The client sends the query, the coordinator builds the query plan, distributes it to the workers. The workers execute the tasks underlying the query in a pipelined fashion, okay, and running in a multi-threaded manner. And then using a variety of plugins is able to work with the data in a variety of storage or persistence forms. Okay, so as I've said, Presto is very high performance. The question then is, why is it so fast? So we talked earlier, one of the key things is it's an in-memory parallel queries. And that in-memory is very, very different, much, much faster than the MapReduce used by traditional Hadoop applications. Pipelining is a key aspect as well. Working with the data locally on the worker nodes with multi-threading, caching, okay, and also the just-in-time compiler, and the SQL optimization that it does before it distributes the queries. And then other optimizations exist. One powerful one is predicate pushdown, and that allows the query predicates to be pushed down to the data persistence layers to be able to execute more quickly with the local data. All right, so just to contrast Presto with the traditional MapReduce, as most of you probably know, MapReduce has a chaining of map steps that transform data and then reducing steps that aggregate or pull together. But that chaining, that handoff between the map step and the reduce step is with disk I/O. Okay? And this causes not only slower latency, but it also means that the map and the reduce steps or the reduce step is waiting for the map step to complete. So there's extra time wasted while the reduce step sits there and waits for the map steps to finish. So to get away from that, Presto avoids disk I/O. The worker nodes run the tasks and the querying totally in memory. And that avoids the wait time. There is no separate map and reduce step, no step waiting for the previous step. And everything is running in a pipeline fashion, so there's no delays at all. Okay. All right, so how do you use data in S3 with Presto? Well, any table that you've declared within the Hive metastore is immediately accessible and queryable by Presto. Okay? And that, of course, includes data that's in S3 exposed via create external table. So I showed you in an earlier slide an example of that, but we'll actually do that in the demo. All right, so once a data source is declared within the metastore, it's available to Presto. You have a variety of ways in which you can deploy the metastore for testing, development and unit testing. You can use an embedded mode where everything is contained within the same JVM. A better mode is a local mode where you decouple the persistence from the JVM. So you have a separate process for the persistence. And then a fully decoupled mode called remote mode allows the metastore service and the persistence to run in their own processes, and then clients running in their separate processes, talk to the metastore service. So that gives you more flexibility in a variety of clients, et cetera. A list of data sources that Presto works with, and there are others as well, but you've got Hive, of course, NoSQL stores like Cassandra, MySQL and Postgres, a couple of relational ones, and some pub-sub communication or messaging hubs. Okay, so you've heard what Presto can do. The question is always, when do you use it and when might you not use it? So when you might use Presto, where it would be recommended, is if you have a need for fast and interactive query capabilities with a large number of concurrent queries running. And also if you have a high demand for ANSI SQL. Where you might not want to use Presto and maybe use other technologies is if you're doing primarily batch processing, especially in a mission critical fashion, where you're doing some ETL, some transformation of the data, enriching, aggregation, et cetera. In that case, you can use Hive, which is it's an older but more established tool. It's less capable on the querying front, but it's much more powerful in terms of being able to transform the data. And of course, the rising star these days is Spark. Spark gives you a lot of capability to do ETL and process the data. Also, if you're going to do more than just query the data with SQL, if you're going to actually take the results of that query and then run some computation over it, Presto will not do that. Presto does have functions, it even has some user-defined functions, but its real strength is in the SQL querying capability. It gets you the data. If you actually want to compute over the data, things like machine learning and doing other algorithms like graph algorithms, then Spark is probably the best bet there. Spark with Spark SQL can interface with data stores declared in Hive, for example, but it has a whole bunch of libraries and modules for doing machine learning and other computation. And then finally, if your data is primarily, if it's well-defined and it's primarily of a star schema format, where you've got a fact table and then dimension tables, if that's the primary form of your data and you've got a limited diversity in the data types, then probably using a traditional data warehouse might be a better way. And Redshift would be the recommendation there. If you want to expose a web UI for your users to talk to Presto, a popular one is AirPal, developed by Airbnb. Whole host of features, including access control for users. You can find and discover the tables that have been declared. You can look at the metadata and even look at sample data from the tables. There's a query editor that makes it convenient. And you can submit the queries through the web interface and track the status of those queries and how they're progressing. Once you've got results back, you can export them as CSV. You can create Hive tables directly from the web UI based on the results that you get back from some query. So you can create a new table from that. You can also save the queries and go back to them later and browse through them and re-execute them. We have a CloudFormation template that allows you to spin up an EC2 instance with AirPal and configures it to talk to your EMR cluster. So if you're looking to deploy AirPal, there's a convenient way to do that with a CloudFormation template. All right, so let's actually execute some queries. I think our cluster should be up and running now. So let me just refresh here. I guess it's still, no, we've got 6 nodes. That's probably enough to get going. 6 nodes of the task nodes. Task nodes, I didn't explain those before. Task nodes are primarily CPU and RAM. So you don't add task nodes to give you disk space. There is some local disk space, but it's primarily there to boost the aggregate CPU and memory for your cluster. So you can add as many task nodes as you need to be able to complete the processing in a shorter period of time, for example. Looks like we've got 10 nodes now running. Okay, so let's actually, before I do that, let me go into S3 and show you the data we're going to work with. All right, so we've got flight delays. Yeah, flight delays. All right, so as I showed you in the slide, we have a bucket called flight delays. This is from the Department of Transportation. Their air flight statistics from 1987 to 2015, 29 years worth of data. It was originally in CSV format, and as I said, I partitioned it into years. And within each partition, there's a CSV file that's been bzip2 compressed. But what I've also done is converted that data into Parquet, similarly, using partitioning. But here we have the data in Parquet, which is column-oriented, which gives us an extra boost in performance. So that's where the data lives. we haven't transformed the data. It's in its original form. So let's go to EMR. Here's our cluster. And we're going to SSH into the cluster. So we click on that link and get this handy command. It's telling us how we can do that. Let me go to my terminal. Let me see if I can make this larger. All right, let's try that. Is that readable? All right. All right, so I'm SSHing into the cluster. And it gives us a splash screen letting us know we're on the cluster. It's using the SSH key that's stored on my Mac, so that's how we deal with the security. So what I'm going to do is I'm going to run Hive. And this is where we're going to declare the existence of this large data set on S3. So for that, I'm going to grab So I have this as an exercise, and I'll share the shortened URL for this late at the end if anyone wants to go back in their own account later and try this. But we're going to take the create external table commands here. Actually, this is probably, okay, that's the CSV version. I'm going to grab the Parquet version. So we're just going to copy and paste this into Hive. So you see in bold at the bottom, we've got partitioned by year, those year equal partitions, stored as Parquet, the column oriented, and we're indicating where it lives. So I copy that. Oops. Go here. All right. Paste that. And again, I'm not creating a table I'm not populating a table. All I'm doing is saying data exists elsewhere, interpret it in this way. Okay? So this is the schema on read. When we actually run our queries, the queries will leverage this metadata, if you will, for that query to be able to work with the data. Okay, so Hive now knows about that table. We can say show tables. And so you can see the tables, air delays _par, the Parquet version. We can even do describe table. Actually, I don't think I need table. Air delays. So there's the metadata associated with this table. So Hive knows about our table. The one last thing we need to do is to tell the Metastore, MSCK, Metastore check, to repair. It's not really repairing, but what it's doing is air delays par. What is, let's see, table's not, what did I, yep. It's my dyslexic fingers. Air delays par, okay, there we go. So what that's doing is essentially synchronizing things so that it's aware of the partitioning in particular. Okay, so Hive now knows about the Hive store, Metastore continues on, even though I've exited from the client. Now what I'm going to do is run Presto, see the command line for Presto. Okay. And we're going to tell it to use Hive default. That's the table space that we have, okay. And now what we're going to do is run some queries. So I'm going to take the, let's see, let's do this here. So we're going to try to answer the question, given this large data set, 29 years, it includes it's got like 115 columns, so it's a wide table. It's got all kinds of information about delays, flight delays, which airline carriers, which origin airports, destination airports, et cetera, a whole bunch of information. But we're gonna, and timing information. We're gonna ask the question, which months have the greatest number of delays? So we have a query for that. So we're gonna do a group by, so it's an aggregation. Let's go to our terminal, and I'm gonna paste that there. Boom. So you can see it's pretty quick, 29 years. This was just 10 nodes. Of course, you could get higher parallelism with more nodes in the cluster. But it gives you, typical SQL type capability here. It also gives you some statistics at the bottom. I'm not sure if you can read those. So 167 million rows. And the speed was 15 million rows per second. So it's not too bad. Okay. All right, let's try one last query. This time we're going to ask the question, which carriers, airline carriers, have the most numerous departures? Okay. So paste that in. Now you can see, so here are the different, these are the short form carrier designations, the number of delays. But one of the things you'll see is there's actually a boost in speed now, 35 million rows per second, due to the caching and other internal optimizations. All right, so, and you could play around with the data in a variety of ways, doing ad hoc data exploration, et cetera. All right. All right, so in summary, about Presto on EMR, querying data in S3. Data in S3 is queryable in using Presto on EMR. You don't need to do any additional structuring or creation of schemas, populating tables, any of that. It's immediately available for querying. Presto is trivial to deploy on EMR. That checkbox will do it. You may know that you can launch an EMR cluster from the command line, so you can automate that process. Using Presto is simply a matter of a parameter. It says to use Presto as one of the many applications. Presto, as you saw, we could run some ad hoc queries and do some data exploration very quickly. It uses a variety of data sources, fast performance due to the in-memory processing and the pipelining. It's feature-rich, and it's increasingly being adopted in production. We have it marked as a sandbox application currently within AWS, within EMR, but in fact, a number of companies are using it in production. You saw the Netflix example, but other companies like Facebook and Airbnb and a whole host of other large companies are in fact using it in production. So it's still early days for Presto, but it's already proven its capabilities. Okay, that's it. Some references there if you want to explore some other things. You can copy the shortened URL down if you want to go back later and with your own AWS account and try out that exercise. The exercise that I have there does two things. First, it declares the CSV table, and then shows you how to create the Parquet formatted and Snappy formatted version of that for the higher performance. Shows you how to do that in a shorter way. So it's got some additional things, but it's essentially what I showed you today. And last but not least, please complete evaluations. And I'll take any questions. Oh, thanks.
Is regarding Spark compared to Presto.
Right.
Could you go into a little bit more in terms of the streaming issues that you were discussing? Because the way you described it is not how I've experienced where Spark's strengths are versus Presto. So maybe just take a minute or two just to expand on that.
Well, the fundamental difference is that Presto is a query engine only, so it executes SQL. Spark does SQL queries and a whole host of other things. As I mentioned, if you're going to do computation on the data, machine learning, et cetera, Spark is the way to go. It's going to give you a much more complete. Now, in terms of performance, Presto actually works faster than Spark SQL. Spark SQL works at about the same speed as Hive. So it's leveraging some of the same components as Hive. But it probably will get faster with time as well.
One of the things they've worked on with Spark is to reduce the errors. What is the situation with errors with Presto?
So Presto is not fault tolerant. That's where I mentioned if you're going to run mission critical batch type processing, that's where working with something more mature like Hive is the way to go. Presto, as I said, is not fault tolerant. It's getting better and will get better with time, so it'll be able to handle things better and errors in particular. But Spark is probably more robust in terms of error handling.
Thank you.
Yep.
Hi. Thanks for the nice presentation. So one question for EMR clusters. There's an option to create different instance type for different type of nodes. Is it a good idea for have like M1 for master node than R3 for core node?
Yeah, the master node isn't doing a lot. It's certainly not doing much in terms of computation. And the core nodes are primarily for managing HDFS data. So those you can use mainstream type M1 type, maybe M3s for the cores because of the additional RAM. If you're working with very large data sets, particularly in HDFS, then the name server needs to have enough RAM to because it has to hold the directory to all the objects in memory. So you'll need enough RAM for that. For the task nodes, that's where you're doing computation, so CPU and RAM. Those, you're probably best to use things like M3, maybe M3 4x large, M3 8x large, depending on what you're doing. And as I mentioned earlier, if you're doing Spark workloads or memory-intensive workloads, including Presto, going with memory optimized, like R3s and M4s, those are memory optimized. Those would be recommended for those kind of workloads.
Yeah, so right now we are using Spark, and for Spark we are using R3 2x large. But we are creating for master, core, and tasks, all are R3 2x large. So according to you, we can use M for master and core, and then R3 for tasks, right?
Yep.
Okay.
Yep.
Thank you.
Any other questions, comments? If not, thank you very much, and be sure to fill in your evaluations.